Hello everybody and welcome back. We're going to continue on looking at the 2013 Hypatia contest in this video. We're on to question number 2. A parabola has equation y equals x minus 3 squared plus 1. We have 4 parts to this question. The first 3 are light bulbs. A part, what are the coordinates of the vertex of the parabola? Well, fortunately they've given us the parabola in vertex form. So I'm pretty sure that's the parabola, but let's just double check. Yeah, x minus 3 plus 1. When it's written in vertex form, which will be x minus h squared plus k, then the vertex is given by hk. So if you've never seen vertex form, here it is. So the vertex of the parabola is just hk. So if it's a times x minus h squared plus k, and here we have minus 3 plus 1, so our vertex is going to be 3, 1. Fairly straightforward first part of the question. Vertex form of the parabola, last I checked, is 10th grade level math, so should be something that we're familiar with, and that's probably why it's a light bulb question in part A. Alright, B part. A new parabola is created by translating the original parabola 3 units to the left and 3 units up. What is the equation of the translated parabola? Okay, well, they don't tell us what equation we need to use, so I think it's best to probably just stick with the vertex form of the parabola. Okay? So, if we have vertex form of the parabola, and maybe this is, 3, 1, and our parabola comes down like this, then when we translate it, it's going to look something like, if we translate it, then its vertex is going to be translated as 3 units over and 3 units up. Was it 3 units to the left or 3 units to the right? 3 units to the left and 3 units up. Okay? So let's redraw this. Actually, you can redraw the whole thing and I'll just use a different color for the translated parabola. So we'll say this is 3, 1, and here's our parabola. Now if we're going to translate it 3 units over, three units left, and then 3 units up. Then we're going to get a brand new parabola, and we can tell exactly what its vertex will be. And from its vertex, oh, that's just an awful parabola right there. Now, since the we're only translating it, so it's never stretched. Can't spell today. Stretched. That was embarrassing. How do you spell stretch? No, I think there's no extra T in there. It's just stretch. Alright, so our new vertex is at, well, we go to the left by 3, so we subtract 3, and then we go up by 3. So that's 0, 4. So 1 times, and then it's x minus 0 squared plus 4. Well, that's just x squared plus 4. And that's our final answer. Y equals x squared plus 4 is the equation of the parabola. Okay, let's just double check. 3 units to the left and 3 units up. All right. Now, C part. Determine the coordinates of the point of intersection between these two parabolas. Okay. So our point of intersection, at least on our little diagram, is right here. I don't know how accurate this is, so it might not occur in the second quadrant. It might be somewhere in the first. But in order to determine the point of intersection, we just need to set these two parabolas equal to each other. So x minus 3 squared plus 1, well, that's equal to y, and the y value should be the same on both for the point of intersection. So we can set that equal to x squared plus 4. Let's expand this one out. X squared minus 6x plus 9 plus 1 equals x squared plus 4. These two x squareds, they're going to cancel each other out. And we're going to be left with 10 over here. We can subtract off 4. Equals 6x. So 6 equals 6x. And that just means that x is equal to 1. And y, we can find y by plugging 1 back into either formula. It doesn't really matter which. So we get y is equal to 5. And we could just try and double check that mentally here. 1 minus 3 is negative 2. Negative 2 squared is 4. 4 plus 1 is 5. So 1, 5 is the point of intersection. Okay. Now, it's really nice because just because we've translated and we never stretched it, the a value stayed the same. So the coefficient of the x squared is the same in both parabolas, and that means that they will just intersect in a single point, rather than 2 points if one of them somehow got stretched into a different a value. All right, the last part of 2D. The parabola with equation y equals ax squared plus 1, with a less than 0, touches the parabola with equation y equals x minus 3 squared plus 1, so our starting parabola, at exactly 1 point. It touches. Okay. Determine the value of a. Okay. Let's draw ourselves a little picture just so that we know sort of what's going on. So here we have 3, 1, and then we have a brand new parabola. We'll use red here. And he maybe touches right here, and it goes something like this. It's something like that. Because A is negative, so our coefficient A is negative, we know that the parabola is facing down. Okay. So what is the exact equation? Ax squared plus 4. Okay. Touches the parabola. So their intersection point, they'll need exactly one intersection point. So this one's ax squared plus 4. A is less than 0. And this one here is x minus 3 squared plus 1. Okay. So they need to have exactly one intersection point, and that will be the point at which they touch. And we'll just take it on faith that they won't intersect transversely. Yeah, if they intersected transversely, there'd have to be a second point of intersection. Oh well. So what's going to happen is we're going to set these two equations equal to each other, and we're going to rearrange. But because the a values are different, this first parabola has an a value of 1, whereas this one has an a value of something that isn't 1. We're going to get ourselves a quadratic equation that we're going to need to solve. But a quadratic equation will give us two values of x. So that means two intersection points. Unless that quadratic equation happens to be a perfect square of some sort. Alright. So how do we handle this? Ax squared plus 4 is equal to x minus 3 squared plus 1. So we're left with ax squared plus 4 is equal to x squared minus 6x plus 9 plus 1. We already saw that in the last time. So we can say x squared minus x squared minus 6x. We're just bringing everything over to the other side. Plus 10 minus 4 equals 0. So we'll have 1 minus a x squared minus 6x plus 6 equals 0. Okay. And what we want to do is turn this into a perfect square. And so if you understand what I'm talking about and as to why a perfect square will work, fantastic. Maybe if you tried this, you did it that way, but we can always fall back on the quadratic formula if we're a little confused or if we just don't know exactly when quadratics have exactly one root. And we do need exactly one root. One value of x gives one intersection point. So let's do it the less elegant but still completely correct and completely valid way. We'll use the quadratic formula. So we'll get negative b plus or minus the square root of b squared, so that'll be negative 6 squared, minus 4a, so that's 1 minus a, c, all over 2a. Okay. That's 6 plus or minus, and we'll have the square root of 36 minus 24 plus 24a, all over 2, 1 minus a. 6 plus or minus square root of 12 plus 24a all over 2, 1 minus a. And now here's where the fun begins. We need to have exactly one root. So we need to have exactly one point of intersection, but any root to our any solution to our quadratic formula is going to give us a point of intersection. So we need there to be only one solution. And that means whatever's in the square root sign needs to be 0. Right? Notice that, say the square root sign wasn't 0, so whatever's under here isn't 0. We could get a square root of 5 or negative 2 or negative 0.2 or something like that. As long as this value isn't 0, we're going to add it to 6 and subtract it from 6. And that's going to give us two different values for the numerator. The denominator, whatever it is, it's fixed, and that would mean two different x values. So the only way to get the same value is if we add 0 to 6 and subtract 0 from 6, and that'll just give us a 6 on top divided by whatever this is. Okay? If we have two different values for the numerator, we're going to get two different x values. That means two different intersection points, and we need exactly one intersection point. And that means we need exactly one value for x, one value for this expression, and that means one value for the numerator. So the numerator is going to have to be 6. And that means that square root of 12 minus 24a is equal to 0. Square root of 12 minus 24a is equal to 0. Was it minus 24 or was it plus? Yeah, it's plus. So we have a little plus sign here. A little plus sign here. Square both sides. And that means that 24a equals negative 12. And that means that a is negative 12 over 24, which is negative 1/2. Now, were we asked for the value of a, or were we asked for the value of the intersection point? Okay, we just asked for the value of a. So all the steps that we took, we set up our equation for the intersection. We got a quadratic, and we said this quadratic needs to have only one root, and we justified it. We justified exactly why we need only one root. Otherwise, we might get two roots, and that would be two different points of intersection. Well, if you want exactly one root to a quadratic formula, because we have the plus and minus, the discriminant, which is this part in here, is going to have to be 0. So square root of 12 plus 24a needs to be 0, and that gives us exactly one value for a. And we put a little box around our answer, and that's it. If we wanted to, we could double check by plugging this in and finding exactly what that x value is, and then figuring out what the y value is, and we could get our single point of intersection, but that's not what we're asked for. We don't care what this is, this point of intersection is, we just care about what a is. So a is negative 1/2, and it tracks. A was supposed to be a negative value. Well, we've got a is less than 0. So that's just a little minor check we can make in our heads before we move on. And that was question number 2. So hopefully you enjoyed it, and I'll see you guys next time for question number 3. Thank you so much for joining me.